So the beta particles have medium penetrating power. So like a thin piece of aluminum foil would protect yourself from beta particles. Now the gamma particles are much more dangerous. These are high energy waves. So high energy waves. Another thing about gamma particles is they are always produced along with alpha and beta particles. So if you've got an alpha or a beta particle, you also have a gamma particle traveling with it. These have no charge, so I'll put none under charge. The symbol for a gamma particle, it looks like a diving alpha particle, really upside down alpha, and it has 0, 0. That means no mass and no charge. That's the nuclear symbol, and the Greek symbol is just the Greek alphabet for the G, gamma. These have very high penetrating power. You need at least 3 feet of concrete or several inches of lead to protect yourself from a gamma particle. Very, very dangerous. Then we have neutrons. Really, the only thing about a neutron I want you to remember, we know that neutrons have no charge, so we'll put none under charge. And these are actually not emissions, they're just some symbols you need to be familiar with for your balancing your nuclear reactions. So the symbol for a neutron, we learned that a neutron has a mass of 1. They're neutral, so they have no charge, and we just put it in. There's 2 more symbols that you need to be familiar with. Positron and a proton. So let's finish this part off. Positron is also known as the anti-electron. So basically, it's the positive equivalent to an electron. So its charge is positive. And the symbol that we use in the nuclear equations, when balancing them, is a 0, positive 1, E. So it's kind of like a beta particle, since the beta particle is an electron, but it's positively charged. And then, of course, we have a proton. We learned that protons are positively charged. The proton is what makes every element unique. It uniquely identifies every element. And the symbol we use for the proton is 1 over 1 H. It's the same as the hydrogen nucleus. All right. So these are the emissions or the symbols for the particles that we will need to be familiar with in our nuclear reactions. So let's talk a little bit about what a nuclear reaction is. When nuclear reactions occur, a process called transmutation occurs. And when something mutates, it's changing identities. So in other words, your nucleus is changing, which means your number of protons are changing. So transmutation occurs if there's a change in the number of protons within the nucleus. So for example, we have uranium-238, and this will be over 92. Couldn't put both of those into my PowerPoint. And then thorium is over 90. And then we have it producing, this is an alpha particle, 4 over 2 He. Let's fill that in. In a nuclear reaction, we call the starting materials the parent nuclide. That's PARENTNUCLIDE. And then we have where the product, the new element that is formed, that is referred to as the daughter nuclide. And remember, y'all, these are the nucleus or the nuclei of the atoms. So I'm not going to change. And this is the emission. And this emission here specifically is an alpha particle. When you're balancing a nuclear reaction, you're just making sure that the superscripts on the left total up to the superscripts on the right, and the subscripts on the left total up to the subscripts on the right. So treat your yield sign as an equal sign. And let's just look at this. You have 238 is the only superscript on this side. And so if you add up the superscripts on the product side, 234 plus 4, that does in fact give you 238. Look at your subscripts. 92 is the only subscript over here. So 92 equals 90 plus 2. So 92 and 92. That's how you balance a nuclear reaction. You're making sure that the superscripts on the left equal the superscripts on the right, subscripts on the left equal the subscripts on the right. So let's take a second to take a look at this first example. This is copper 66 over 29. You're going to need to fill that in. And you'll need your periodic table for this as well. So make sure you have your periodic table out. This is emitting this will be a beta particle. I'll put it here, a beta particle. So let's figure out what the daughter nuclide is going to be. Here's your yield sign, your equal sign. So the only superscript on this side is 66. So that means both superscripts on this side have to equal 66. Well, this is a 0, so 0 plus 66 gives me 66. And this is a -1 subscript. So -1 plus what equals the 29? Well, -1 plus 30 equals 29. So now you're just going to look at on the periodic table and find atomic number 30. So as you look on the periodic table, searching for atomic number 30, try to line this up. There you go. It's kind of difficult on the zinc is atomic number 30. So that means that this is Zn. You would identify the daughter nuclide after you get your superscripts and subscripts filled in. All right, so let's look at example 2. Here we have lead 204 over 82, and it's emitting an alpha particle. This is an alpha emission, 4 over 2 He. So here's our yield sign. The only superscript on this side is 204. So 204 equals 4 plus what? That's right, 200. 200 plus 4 is 204. And on the subscripts, 82 is the only subscript on this side. So 2 plus 80 equals 82. So that means this element is element number 80. So again, look on your periodic table, and you'll find on your periodic table element number 80 right here, mercury. So you would identify this one as Hg. Okay? We will do these in class together. The last thing I want to talk about is half-life. And we're going to practice some calculations with half-life as well in class. Half-life is pretty much what it sounds like. The symbol is T with a 1/2 as a subscript. It is the amount of time needed for 1/2 of the original amount of a radioactive isotope to decay. All radioactive substances have half-lives.